Let's discuss a question on thermodynamics. So we have 4 cycles given as 4 options. We need to find out which of these cycles do positive work done. Well, now before going to the question, I would like to just give you some basics. That work done formula is quasi-static work done formula is given by integral PdV, and heat added to the system is given by integral TdS. So when the volume is increasing, you say that the expansion, when the volume is increasing, you say work is done by the system, and if volume is decreasing, work is done on the system, so which is a compressive thing. So work done by the system, it's an expansion process. And similarly, the same thing can be made out from this formula, when entropy, which is entropy is increasing, then we say that heat is added to the system. Now, keeping these two facts, let's go to the figure. Now here, let me just explain. The top half, volume is expanding, so work is done by the system. The top half is therefore an expansion process. The bottom half, because the arrow is like this, volume is decreasing, so you say it's a compressive process. Work is done on the system. Now the area under the top curve is more than area under the bottom curve, and the difference is the area under the curve, which is nothing but the work done by the system, because the top area under the curve is more than, so this is the top area, and the work done is this entire thing under this area minus this entire thing, which is the compressive work. So you get the total positive work which is done by the system. Okay, and this is just an example. I mean, if you have a clockwise cycle, the arrows making it a clockwise cycle, it's basically the work is done by the system. This happens in heat engines, all the cycles which produce work, Brayton cycle, I mean the heat engine, or the Carnot cycle of heat engine, all your steam turbine cycles. Okay, all this work on it. So this is definitely an option which produces which has positive work done on the system. Now coming to figure 3. Figure 3, well, obviously whatever I have explained, so going by that, the work, if you look at the top half which produces more work, top half, the arrows is anti-clockwise, so volume is decreasing, work is done on the system, which is more than the work done by the system, because here in the bottom half, volume is increasing, so work is done by the system. So if you subtract that, there is more work which is done on the system, which is compressive work. So here effectively work is done on the system, so this is not the option. Now coming to this, the other the figure 2, which is a TS cycle. Look at the top half again. The top half, if you look at it, the entropy is increasing, that means heat is added to the system in the top half. In the bottom half, the entropy is decreasing, that means heat is removed from the system. But effectively, if you look at the net heat, the area under the curve, because it's integral TdS, which is integral ydx, so it's something like that. So the top half is, the heat added is nothing but the area under the top curve with the x-axis. Obviously that area is more than the area made by the bottom curve with the x-axis, which is the entropy axis. So effectively I can say that heat is added to the cycle, that there is a net heat added to the cycle. The first law of cycle, which is integral dq is integral work done, that is the net heat added in a cycle is equal to the net work done by the system, because it's a cyclic, for the entire cycle there is no change in internal energy, so the net heat added should be equal to the positive work done by the system. And the figure 2, because we have concluded from this explanation, from the explanation just I made before, that net heat is added to the system. So obviously when net heat is added to the system, work is done by the system. So here also you have the work done by the system. And this is again example for your Carnot cycle of heat engine, or your Otto cycle. Whenever you see you have a clockwise arrow, which means that work is done on the system. Okay, and whatever I have explained, this TS diagram which is in figure 4 is just opposite to the, here there's a heat, I mean the work, the heat is rejected in the top half, which is more than the heat added. Because why is heat rejected in the top half? Because entropy is decreasing, and in the bottom half entropy is increasing, so heat is added. So if you combine that, effectively net heat is taken out from the system, so work is done on the system. Going by this only, when effectively there is a work done on the system, heat has to be rejected. Effectively when heat is added to the system and cycle, work has to be done by the cycle. That is the simple case. So 1 and 2, figure 1 and 2, you have a positive work done. I think this explanation you should remember for always. Whenever all these cycles are given and you need to decide work done, just split it into different processes, and whatever explanation I have given, try to follow that. So option D is the one, because figure 1 and 2 both produce work done. Thank you.